make 1-phenyl-3-hexanol. It was one of the examples that I'm pretty sure, like 96% sure that we didn't go over when we were doing chapter 15. So, if you practiced that one or if you tried that one, here you go. Looks like that. So, anyway, continuing with aldehydes and ketones. So, yesterday we left off with reaction themes 1 and 2, where I showed you exactly the same thing, or at least what. Okay, yeah. At least what results in the exact same thing, right? Because once you do this, you can just work that up with acid. Or honestly, if this is strong enough, no, hydroxide is a stronger base than, I'd have to check pKa's to know. But you can at least use a weak acid to work this guy up and turn it into the same thing as this. So, what's the actual difference between these two guys? Because I told you yesterday, basically, you can always start here, and you'll get what you're going to get in the end. And then you can decide later, oh right, I needed one step before that, and put a little, hold on, tiny step over here before that. And then that has a hydrogen already, and then there we go. This didn't have a negative charge, or something like that. You can correct, you know? But besides just this is a basic environment and this is an acidic environment, what's the difference? Basically, if your nucleophile is strong enough, you can do this. You can attack the carbonyl-carbon. And if our nucleophile isn't strong enough, then we just use acid to protonate our carbonyl, which makes our carbonyl-carbon a better electrophile, right? Because now, excuse me, now instead of having like our valence structures, no charge and then a charge separated one, right? The valence, or the, words are hard. Resonance, thank you. God, resonance. I'm working on the caffeination. So the resonance structure of this one would be charge separated, right? And you'd have a positive charge on your carbon and a negative charge on your oxygen, right? The resonance structure of this, you already have a positive charge over here, so then you would just have a positive charge over here, no corresponding negative charge, right? So basically, overall, this guy has, well, less electron density than this, right? Yes, because we added a proton, and we didn't add any electrons, we just added that hydrogen, the proton. So we've got a positive charge to this guy, no charge to this guy. This carbon, because of resonance, even though we don't have the positive on the carbon, this carbon now, because of resonance, is a better electrophile than it used to be. Yeah? Cool. That's also usually why we write them like this. Mostly just so that when you get to the end, you don't end up with like a negative charge there or a negative charge down here or a positive charge up there. Usually you'll actually have something here and you won't just have to guess if you've got a negative nucleophile or a protonated nucleophile. But yeah, that's the difference between these guys. Okay. from these is that it's really easy to get a chiral center from nucleophilic attack of a carbonyl group, because if I just make one of these guys an R prime, all of a sudden we end up with a chiral center, right? However, we don't actually start out with a chiral center. We start out with this, they call it something. They don't care what it's called. Okay. That's fine. So the starting materials are achiral. The starting materials aren't chiral. There's definitely a name for one of these that's like, if both of those R groups are different, then it's one step away from being chiral, or it's, you know, add one thing and then you will be chiral. There's a name for that. Clearly your book doesn't think it matters, and I write your exams from the slides and the test bank, so that's cool. But let's talk about selectivity, because can we get selectivity from this? It's not really the same as in, SN2 attack or anything, right? So really we've just got a flat guy, and it's going to be attacked from the top or from the bottom. We can't really control which way, right? It's just all up in a solution. So we're always going to get racemic mixtures from these guys. And again, not all products of these kind of reactions are going to be chiral, because these two R groups could be the same. It's just usually they're not. There's more ways to make them different than the same. So often you're going to get a new chiral center, and you are not going to be able to control your chiral center this way, which means probably don't use this for making pharmaceuticals, because did you guys, I always try to reference things like stories, and then I remember I heard of this story in undergrad organic chemistry, so it's probably up to me to share it with you guys. There was if I remembered that ahead of time and didn't just bring them up, I could, just toss it out there, but, chiral morning sickness. Okay. Thalidomide. Thalidomide was a drug that at some point was prescribed widely to pregnant women for morning sickness, and no one realized it was chiral, and so they just, nobody made one specific, what is it? Not orientation. What are they called? Chiral.
Enantiomers?
Yeah. Enantiomers or diastereoisomers if they've got two, right? Two chiral centers, and enantiomers if they've got one chiral center?
Usually.
Yeah. Enantiomers are mirror images, which is why we have to have another name for when they have two chiral centers, because you could have the mirror image, but you could also have the one that's not overlappable, but also not the mirror image if you've got two different chiral centers, because you can switch one and not the other. So they had to come up with another name, and that was diastereomers. So they didn't bother making one enantiomer, and it turns out the left-handed molecule was really effective, and the right-handed molecule was really, really toxic. Like babies being born without all of their limbs kind of toxic, and then they learned. I assume this somehow got through FDA or got through its preliminary testing, because it was being made one way that was maybe selective or something, and they didn't notice. And then once they started producing it, on a bigger scale, they made the racemic mixture because they didn't think about it being chiral. But yeah, so pharmaceuticals, your body is very, very chiral. pharmaceuticals are really important when there are chiral centers. So this stuff, not suitable for that, generally. Okay, so let's talk about the addition of several different carbon nucleophiles. We'll do some examples. So, with all of these carbon nucleophiles, these are strong enough nucleophiles that we're not going to have to protonate. So, they're going to follow this two-step pattern of nucleophilic attack, make the bond between the carbon nucleophile and the electrophilic carbonyl compound, and then add a proton so that you're not just stuck in an ion, you actually turned that into an alcohol. Grignard reagents. This is basically, given the difference in electronegativity between carbon and magnesium, it's a polar covalent bond. Basically, the carbon is really holding on to those electrons, and the magnesium, like most metals, is kind of like, it's fine, you can have those, whatever, which is why metals can conduct electricity so well, because all the metals are just sort of clumped together, and they're all kind of going, whatever, the valence electrons can be everybody's, and so if you put a current through it, they just share them with everybody, and they let them all go. So, basically, the carbon bears a partial negative charge. They're really good nucleophiles. We already talked about how they're really good nucleophiles. So let's just try it. Formaldehyde, yeah, let's do this. Let's do this in a mechanism. That's our electrophile, and this guy is our nucleophile, right? So, first thing we're going to do is nucleophile is going to go ahead and attack the electrophile. And because we've got a carbonyl and we don't have, like with your other nucleophilic attacks, you'd have to have a leaving group, right? And so you'd either, is the leaving group good enough to leave when you attack, or is it a good enough leaving group that it leaves by itself, and then you can attack? In this case, our leaving group is always these pi electrons because, I mean, you've got a double bond, but the carbon and the oxygen will be just as, not just as strongly attached, but they'll still be bonded to each other. They'll still be sitting right in the same place if we move the pi electrons off and they're just single bonded, right? So those are the easiest electrons to move. So we have this, we have I'll do that. And that was the electrophile. This was the nucleophile, and counter ion can hang out over here. Although, you don't have to write it because, I don't know, I mean, who cares? Not me, it's metal, so. Metals don't matter in organic chemistry. That's a lie, but you know. Okay, so we get that. And then, what's our next step? Oh, it's up there. Okay, fine. I'm over here trying to quiz you. All right, so then we're going to protonate this with acid, right? So, I'm gonna write H3O plus in my weird way so I can do arrows. I'm gonna get marker on myself whether I leave these uncapped or not. And we're gonna do if I had thought this through better, I might have picked blue as my electrophile because I think blue might have gotten ruined less quickly than the green from writing over fresh black marker, but that's okay. It's fine. And then, sure, if we want to finish that, we can go like this. And okay. Yeah, you're, yeah, that's what I thought. Okay. Yeah, I don't like how up there it goes, hey, also you have Mg2+. This is part of why I don't like writing, or I guess this gets brackets. This is part of why I don't like writing these things, because where's the bromine go? I mean, it doesn't really matter where the bromine goes because what we care about is this stuff, but if they're gonna write that, include everything or just get rid of the stuff that doesn't matter, is my opinion. Because, I don't know. I'm sure I could guess where the bromine goes. I mean, I definitely could. The problem is that I can give a really convincing and reasonable sounding, honestly, probably reasonable explanation for why the bromine goes where it goes for several different answers, all of which are contradictory. So I'm really good at explaining why the wrong answer is correct, as well as the right answer is correct. So I don't want to explain this to you without actually knowing which one's correct. And it doesn't really matter, so whatever. Get rid of that stuff. This is what we got. Yeah? What did I unhide this? This is exactly the same thing. Okay. Oh, okay. They're saying that if you have an aldehyde that's not formaldehyde, if you have an aldehyde that's not formaldehyde, and you use a Grignard reagent on it, you're going to get a secondary alcohol. If you use a ketone, you're going to get a primary alcohol. These are the kind of things that it's easy to make flashcards on, but I would prefer that, like, to me, this knowledge is incidental. As long as you know you can take this and attack your electrophilic carbonyl carbon, and you end up with 4 bonds to it, and you need to protonate that, you're going to figure out if it's a secondary or tertiary alcohol, right? So this is a thing, but these are the kind of things that I would prefer us not memorize, because that feels like a waste of time and effort. Okay. Let's see. Several things to do, but go ahead and try this. Actually, don't go ahead and try this, just because I forgot to actually look at your worksheet for recitation today, and I told your TA that we don't go over most of those examples so we can use them. So, just in case. If you ever want any of these examples or problems that we have in the slides, if you ever want someone to go over them, I can during office hours. You can ask the peer tutor that we have. We have a peer tutor. They only do virtual appointments, but you can make virtual appointments, and I think on your homepage I even have a link to more information about that and directly where you can make appointments there. And but my office hours, my TA's office hours, or honestly, if there's time in recitation, you can do that too. Yes?
Did you find out if we can move recitation to this room?
We are going to, because I don't know who to ask, but to be honest, all of the people I can think of to ask would tell me, they would tell me the exact same thing that I want to tell myself. And it's probably fine, let's do it, and if we get kicked out, whatever. Like, no one, I don't know where the central knowledge is kept, but it is nowhere near the chemistry department, and also nobody knows where it's kept. Like, you would think faculty would know, you know, like, who do you go to find out if a room is available? Well, we go to Kim, but I don't know. Kim only knows, as far as I know, Kim only knows for, like, the Revachol and Crossley rooms. This isn't our campus, this is over here, so I don't know. So, yeah. Moral of the story, higher education, way less organized than you would think it is. Or at least, not everybody knows what's going on with it. Not everybody who perhaps should. All right, let's do addition of organolithium compounds. You know what? We're gonna do a fun exercise where I use blue and I edit this to be organolithium. Because we could do that example, but organolithium compounds do exactly what Grignard reagents do. Now, to be fair, organolithium compounds are going to give you higher yield generally. Sometimes your reaction is like smooth enough, easy enough, there's not enough going on to mess with it that you're going to get high yields no matter what. Sometimes when you do things, you just end up with a really low yield, but if you end up with a really low yield from Grignard reagents, there's a chance organolithium reagents would give you a higher yield. However, depending on your lab technique, there's also a chance that organolithium reagents would give you like nothing, because Grignard reagents are sensitive, remember? We have to make sure that our reaction is entirely free of water, which means, like, it can't be open to the air, right, really? Because air is usually humid, so you kind of have to, like, close things off and make sure you use dry solvents. Organolithium compounds, you have to do all that, and you can't have oxygen in there, which is, like, 12 times as annoying. So, yeah. Because you can use nitrogen or argon to bubble through solvents just to kind of, there won't be as much oxygen in there, you'll kind of get rid of the oxygen, but you can use that really to just, well, I know that this canister of gas is dry, so I'll just bubble that through my dried solvents, I'll keep everything from my dried solvents, I'll keep all the air coming just from this, and it'll be fine because there's zero water. But you're being really lazy about how much oxygen you let in because you're really just using the nitrogen or the argon to have dry air, right? In this case, you can't be lazy about how much oxygen's in there